Dear students, in today's lecture we will study about the parallel operation of AC generators. In this case, if we see as we seen in last lecture that the synchronous generators were connected with the load alone. There was no any parallel generator or parallel load connected in last case. But in this case we will see that there would be some parallel generators connected with a single generator. So generally there is more than one generator operating in parallel to supply the power demand. So now we see what are the advantages of parallel operation. Several generators can supply bigger loads than one machine by itself. So if there are more than one machines, it can supply bigger loads. Another advantage is that high reliability of the power system. Since we know that there are more than one generators, so if any one of them gets a failure, it does not affect the whole system. So the reliability would be quite high in this case. And the third advantage is it allows the removal of one or more of the generators for shutdown purposes or maintenance purposes. So we can easily isolate any of the generator according to our needs. Then we have another advantage, that high efficiency due to operation near full load. So if there are more than one generators, the efficiency would be quite high rather than a single generator. So we will see what are the conditions required for paralleling. Generator G1, this is the G1 generator and this is G2 generator. This G2 generator is connected with the load and this is in parallel to the generator G1. This will be connected as soon as this switch S1 closes. So generator G1 is supplying power to a load with another generator G2 about to be paralleled with G1 by closing switch S1. So as we close the switch S1, this G2 would be paralleled with G1. So there would be some conditions with which G2 would be eligible to be paralleled with G1. So what conditions must be met before the switch can be closed and the two generators connected together? So these are few conditions. The RMS line voltage of the two generators must be equal. This was the first condition. Another condition, the two generators must have same phase sequence. Third condition is the phase angle must be the same. And fourth one is the frequency of the two generator must be about the same. So since we have a condition that this should be about the same, the frequency of new generator called oncoming generator should be slightly higher than the frequency of the running system. In the large generators belonging to power stations, the whole process of paralleling a new generator to the line is automated. So in large generators, we don't need to do this paralleling operation or checking the requirements or conditions by manually. So it is automated. But in the case of smaller generators, the operator checks these conditions manually before putting the new generator in parallel with an existing one. So there's a 3 light bulb method to check the phase of the oncoming generator G2. As the phase changes between the two systems, the light bulbs first get bright, which means there's a large phase difference, and then get dim, which means there's a small phase difference. If all three bulbs get bright and dark together, then the systems have the same phase sequence. So this means if the bulbs get bright and dark at the same time, they would have the same phase sequence. But if the bulbs brighten in succession, then the systems have the opposite phase sequence. Now we will study about the frequency power and voltage reactive power characteristics of synchronous generators. Generators are driven by prime movers, which is the generator's source of mechanical power. As we have already discussed, there are some prime movers like fuel or water turbines, water or something, which are helpful for driving the generators. As the power drawn from the prime movers increases, their speed of rotation would decrease. The decrease in this speed is in general non-linear, but some form of governor mechanism is used to make the decrease in speed linear with an increase in power demand. The governor mechanism is adjusted to provide a slight drooping characteristic with increasing load. We will see this all the scenario in a figure in next few slides. The speed droop of a prime mover is defined by this equation St, where there are two speeds considered. One is the speed with no load NL, and another is speed with full load FL. So this speed droop formula will be used to check the speed of the generator. Now we have two graphs in front of us which shows, this is showing the speed and this is showing the frequency. Both these speed and frequency are on y-axis, while on the x-axis we have the power in both the cases. So the speed versus power curve for a prime mover, similarly the frequency versus power curve for the generator. In both cases it can be seen that at no load the speed was higher, but as at the full load the speed is slightly less. So as the load is connected, the speed starts decreasing. Similarly, the frequency is also decreasing in the case of frequency versus power curve for the generators. So the relationship between frequency and power can be described by this formula, and we have already discussed this formula. In this, FNL is showing the frequency with no load, FSys is showing the operating frequency of the system, and this is SP is basically the slope of the curve. So output power P can be calculated by this simple formula, and we will use this formula in the uh, examples or numericals which deals with the output power of the generators. This reactive power is also similar to the previous case, in which there was a slope and then the voltages of no load and system. But in previous case it was not voltages, it was frequency. This characteristic is not intrinsically linear, but the generator voltage regulators include a feature to make it linear. So this means that it was not actually, ideally it is not a linear, but it has to be made linear with some calculations. Now we go through a simple example in which the figure showing a generator supplying a load, a second load L load 2 is to be connected in parallel with the first one. The generator has a no load frequency of 61 Hz and a slope of 1 megawatts per Hz. Load 1 consumes a real power of 1000 kilowatt at 0.8 pf lagging, while load 2 consumes a real power of 800 kilowatt at 0.707 pf lagging. So we have to calculate the three parts A, B and C. In A part, before the switch is closed, what is the operating frequency of the system? After the load 2 is connected, then what will be the operating frequency of the system? And the third part is, after load 2 is connected, what action could an operator take to restore the system frequency to 60 Hz? The formula for power is given by P is equal to slope into frequency with no load minus the system frequency Fsys. So by this formula we can find the value of Fsys if we know the other three values. So in first part we will find F of the system by using this formula, where we are given with other three values, and we insert the other three values and get the result as 60 Hz. So the frequency of the system would be 60 Hz when there is no second load connected. After second load is connected, we can use the value obtained in the first case as 61 Hz minus 1800 kilowatt. So this 1800 kilowatt would be different because there would be different power in this case. So the answer would be slightly less than the 60 Hz. It would be 59.2 Hz. But we want to keep this frequency constant at 60 Hz, what we need to do? So we need to do that after the second load is connected, the system frequency falls to 59.2 Hz. To restore the system to its proper operating frequency, the operator should increase the governor no load set points by 0.8 Hz to 61.8 Hz so that the resulting frequency would be 60 Hz after subtraction by minus 1.8 Hz. So we conclude that when a generator is operating alone, supplying the system loads, then the real and reactive power supplied by the generator will be the amount demanded by the attached load. And the second case is the governor set points of the generator will control the operating frequency of the system. Similarly, the field current controls the terminal voltage of the power system. We have seen if there is a generator which is connected with large power systems, then the resulting frequency and terminal voltage would be same throughout the power, or we can say the frequency or terminal voltage would be almost constant because the system connected with the generator is very large. This very large system can be modeled with an infinite bus. So we consider there is an infinite bus which is serving us as a large power station. So as a large power station or power systems, an infinite bus is used, and if we see the frequency versus power diagram, the frequency is the same and which is not changing with the effect of the generators. Similarly, the terminal voltage is also constant. So as you can see that from the diagram, the generator is connected in parallel with the infinite bus, which would serve as a very large system, and they are connected to the load. So when a generator is connected in parallel with another generator or a large system, the frequency and terminal voltage of all the machines must be the same. So since their output conductors are tied together, conductors are tied together, therefore their real power frequency and reactive power voltage characteristics can be plotted back to back with a common vertical axis. So this is a common vertical axis, and these are real and reactive power voltage characteristics which are drawn at the same graph. This sketch is usually called house diagram. Assume that the generator has just been paralleled with the infinite bus according to the procedure described previously, then the generator will be essentially floating on the line. supplying a small amount of real power and little or no reactive power. So this is a small amount of real power. That's the case where it is floating on the line. The generator is floating on the line. Suppose the generator had been parallel to the line, but instead of being at a slightly higher frequency than the running system, it was at a slightly lower frequency. As you can see in this diagram, in this case it is slightly on the lower side of the operating frequency. So in this case, when paralleling is complete, the resulting situation is shown in this figure, where the frequency is slightly on the lower side. In this case, as it is written, you can see that it is the consuming case, the case where the power has been consumed. But in this case, notice that there has no load frequency of the generator is less than the system's operating frequency. As seen in this case, if this is the operating frequency, the generator is on slightly, the power is slightly lower than this frequency. The power supplied by the generator is actually negative. In other words, when the generator's no load frequency is less than the system's operating frequency, the generator actually consumes electric power and runs as a motor. So it is to ensure that the generator comes online supplying power instead of consuming it, that the oncoming machine's frequency is adjusted slightly higher than the running system frequency. As we said, that it is ideal that the frequency of the new oncoming machine should be slightly higher than the running system frequency. So many real generators have a reverse power trip connected to them. In this case, it will automatically consume the power back to the bus. So the bus would be consuming the backward power. Has been connected to the infinite bus. What happens when the governor set point is increased? So in this case, the effect of this increase is to shift the no load frequency of the generator upwards. But since the frequency of the system is unchanged, the power supplied by the generator increases. So it is clearly shown in this figure that this frequency has not been increased, so this power has been increased. What happens in this system if the power output of the generator is increased until it exceeds the power consumed by the load? It will, in this case, it will be consumed back by the infinite bus. In second diagram, it is seen that the effect of increasing the governor's set points on generator operating in parallel with infinite bus. In this case, it is seen that the internal voltage EA is same. The voltage of EA is same. As you can see, this is kind of a radius, this is kind of a curve. So since this is a curve, this magnitude would be same, but only the angle would be different. But in all these three different cases, the power would be different. PG1, PG2 and PG3 would be different. So we conclude that when a generator is operating in parallel with infinite bus supplying the system loads, then the frequency and terminal voltage of the generator are controlled by the system to which it is connected. The governor set points of the generator control the real power supplied by the generator to the system. The field current in the generator controls the reactive power supplied by the generator to the system. So the governor set point control real power and the field current controls the reactive power supplied by the generator to the system. Thank you.